Greetings and welcome to another installment of QuantSlob. This is 36, lucky 36 in our basic application series, and this time around we're going to continue on with our exciting summarizing data series with part 8. Very first piece of business right from the get-go. Let's take a look at our previous QuantSlob challenge. So, question. How might we visually display the bivariate relationship between pitch velocity and our original pitch type attribute? First thing we're going to do is we're going to eliminate the not recorded category. Why? Well, because pitch velocity is simply not available for these pitches. Now, I also suggest eliminating the automatic ball category simply because it is so sparsely represented. And it's something of a judgment call, but only 14 observations. Anyway, so to graphically display our numerical attribute pitch velocity by our categorical attribute pitch type, we show the numerical distribution given each category here. And side-by-side box plots are quite well suited for this. And this plot, it may be a little busy, but I think it comes off quite nicely. I created this plot in R. And notice here in this plot, I instructed the software to plot the categories in descending order, left to right, based on the conditional median value of velocity. And remember that summaries are really about comparison. And here we can easily see that four-seam fastballs are the fastest type of pitch in terms of the median value, whereas the very fun ephus pitch is the slowest. Now, when presenting graphs like this, it is usually regarded as good practice to provide the audience with the conditional frequencies of each category. And this plot, as it stands, like I just mentioned, is kind of crowded, so we may not want to further clutter it. But of course, for the sake of presentation, we can always make the tabular distribution of pitch type available here. One last thing before moving on, we could also use stacked histograms to show our bivariate relationship. But especially with so many categories, the side-by-side box plots are to be much preferred, I think. Okay, here we go. The bivariate relationship between two numerical attributes. The graphical summary of two numerical attributes is pretty much dominated by the so-called Cartesian plot. And the idea is pretty straightforward. We have a flat surface like a sheet of paper or a video, which we define with two perpendicular number lines, a horizontal x-axis or abscissa and a vertical y-axis or ordinate. Now, any given observational unit in our data, that is a row in our data frame, will have some value of whatever numerical attribute we're calling x and some value of whatever numerical attribute we're calling y. The pair of values will define some unique point in our Cartesian space here. And we can represent it on our surface in some way, like a little filled circle, a dot, for example. Now, two very popular types of Cartesian plots used to summarize the bivariate relationship between numerical attributes are the scatter plot and the time series plot. Now, for the sake of an example of a scatter plot, we're going to return to our Major League Baseball data set. However, we're going to refactor or transform our data set. We're going to identify what we're going to call prolific pitchers. And we're going to define a prolific pitcher as a pitcher who has, over the 8 years of our data set, thrown 10,000 or more pitches. And it turns out that there are 195 prolific pitchers in our data. And for the sake of clarity, okay, in our original data set, our unit of observation is a game event. In our new transformed data set, our unit of observation is a pitcher. And of course, each big league pitcher, of course, possesses attributes like weight and height. For example, weight versus height of these 195 big league pitchers. Of course, people's weight fluctuates over time. These attribute measures come from fairly recent biographical data on the pitchers. The terms x-axis or abscissa and y-axis or ordinate can be ambiguous. I just want to point this out. Mathematically speaking, they refer to the unique perpendicular number lines that pass through the origin. That is the point x0, y0. Abscissa and ordinate specifically often refer to the actual x and y position respectively of a location or point in our space. Okay, however, in the language of graphics, they commonly refer to the axes that are printed on the plot and define our plot region here. Okay, Now, we have weight on the y-axis, height on the x-axis. We might describe this relationship as weight versus height. In social sciences and psychology, looking at this plot, we might call weight our response and height our predictor or explanatory variable. Sometimes we might call weight our outcome, but the term outcome is often thought of as being reserved for situations where we have a causal relation between x and y. Although really the term outcome for our response, our y value, is pretty loosely applied. In engineering circles, just to mention it, we might call weight our output and height our input, but engineers are used to describing well-defined processes, and well-defined processes are often causal in nature, but still, like the term outcome for weight, in our example, the terms input and output are pretty often loosely used. Okay, now, if we look closely at the height attribute, we notice that it appears that this numerical measure is recorded to the nearest inch. In other words, our domain of height values, at least as far as our data is concerned, contains only integers. And this has a consequence in terms of the quality of our scatter plot. You'll see here there are regions that appear fairly crowded, and in these regions are plot elements. The circles here that identify the weight and height values of some pictures are over-plotted, meaning that one element either partially or fully eclipses another. And this makes it a little challenging for the viewer to get a clear sense of what's happening in these crowded regions. One way to combat this, and one way that I really prefer, is to fill our point elements and use an alpha channel. And this is just a fancy way of saying to make the elements semi-transparent. And in this way, here, take a look. The darkness within a region conveys a visual sense of how heavily represented these values actually are in our data. And it looks like we have here, if you look carefully, a small value of height that sort of stands out from the other observations, along with a fairly large value of height here to the right. So let's take a peek at the distribution of height alone. And this box plot we're using here suggests that these two values are so-called potential outliers. So what is our unit of observation? A prolific pitcher, a person, a human being. And of course, people have names. Okay, one very important feature we look for when examining a bivariate relationship, and one that is often visually conveyed with a scatter plot, is trend, or more specifically, linear trend. And the concept of trend, I think, is something most people sort of understand, but is maybe not necessarily so easy to describe. And one way to think about this is, can we place a line or a line segment through our data that describes the pattern we see? And here the answer is plainly yes. There is a positive linear trend between prolific pitchers' height and weight. Now, upcoming in the next season of QuantSlob, season 5, you're not going to want to miss that. We're going to go into more detail concerning how to calculate what we often call our best trend line, which is what we're showing here in this plot. And the best trend line is the so-called least square solution, or as it is more commonly known, the regression line. Now, all the points don't fall on the line segment here, directly on the line segment. And in most real-world settings, the points will be scattered vertically along our best trend line. The direction of the trend and the degree to which our points vertically cluster along our best trend line can be expressed using a single statistic known as the correlation coefficient, or Pearson's correlation coefficient, named after Carl Pearson. Now, we use lowercase r to notate a sample correlation coefficient. When referring to a correlation coefficient within a population, we commonly use lowercase rho, the 17th letter in the Greek alphabet. Now, these values must always reside in the closed interval -1 to +1. Now, with the correlation coefficient, if we are in doubt as to whether we're viewing our data as representing a sample or a population, and these baseball data are a pretty good example of this, as they can naturally be thought of as a concrete population, but we can also view these data as having been realized from some superpopulation. If we're in doubt whether it's a sample or a population, it's probably advisable to default to using lowercase r to notate our correlation coefficient. Now, here, if all the points lie directly on an upward sloping line, that is, there's no vertical scatter, our correlation coefficient will be 1. If all the points lie directly on a downward sloping line, that is that there is no vertical scatter here, and they're landing on a downward sloping line, our correlation coefficient is going to be -1. Now, there are a couple special cases we want to be aware of. If all the points lie on the same vertical line, which means, by the way, it implies that all the values of x are the same here, or if all the points lie on the same horizontal line, which means, of course, that all the y values are the same, this means that our correlation coefficient is undefined. It's a division by 0 type thing. Okay, now I know what you're wondering here. Well, it turns out in our particular example here, the calculated correlation coefficient for weight versus height among our prolific pitchers is about a half, 0.49. Okay, so before we close out, our QuantSlob challenge, and this kind of requires that you've seen the previous installments in this series. We noticed 2 unusual values of prolific pitcher's height, and a box plot revealed that these are, in fact, potential outliers. Now, recalling how we construct box plots and just using our visual sense, are there any potential outliers of our weight attribute here? We're going to pick this up next time around, along with lots more exciting stuff in part 9. You are definitely not going to want to miss that. That's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.